Today we'll be doing logarithmic functions. And don't forget, when you come back on Monday, I apologize that it's scheduled for Monday, but when we did the schedule, I wasn't even really looking to see when Monday was. It was just, you know, the time to have a quiz. So the nice thing about the quiz that you'll have on Monday is, remember, 31 and 32 is the same topic. It's just rational functions. We spent 2.5 days on rational functions. The other half day being here. Remember, 33 was just our catch-up day where you had a chance to finish the rational functions, and then I gave you like 3 or 4 new questions for you to work on, one with a parabola and one with sort of give me an example of different things. So that will be waiting for you when you come back on Monday. And I want to make sure you all, I say happy Thanksgiving to everybody before you leave today. And if you're traveling, I hope you travel safely and, you know, have a nice break, but not too much of one because we still have 2 weeks left. So we're almost there. Any questions on what's expected between now and when I see you again? Okay. So let's finish up. I asked you to fill in this table because we didn't complete this. This was Monday's notes. And this expression, 1 plus 1 over x to the x, has a funny sort of thing happen to it. As x gets large, notice that the base, 1 plus 1 over x, is just 1 plus and then a number in the decimal area. So in other words, when x is 10, this is 1 plus 1/10, or 1.1 raised to the 10th power. And when you put 10 in, you get this. Remember, these are all truncated. They're all estimations, 2.5937. And some people think, well, as x gets really big, and it's sort of intuitive, you might think that this number gets really big. But as you can see, this number is approaching, this number isn't growing very fast, especially as 10 increases, right? It's only increasing out in the second, third, fourth decimal place, depending on how far we continue to grow this expression, how we increase x. So you notice that it's approaching a number. And that number that it approaches, if we estimate it, is 2.7183, if we estimate it out 4 places. This number has a name. It has a letter. It's called E. And it's a constant. So E is an irrational number. It's a real number, just like any other number. It's irrational, and it's a constant. So in terms of our work with exponentials and logarithmic functions, it's a constant. So it can be used as a base. Just like we looked at the exponential function the other day, f of x equals 2 raised to the x power. We could look at an exponential function where we had e raised to the x power. It's just a constant like 2 or 3 or any other number. Okay? And we call it a natural base because it occurs quite a bit in the applications we're going to be looking at when we come back from Thanksgiving. A lot of problems out or applications in the real world use e as its base. And we'll see that. We'll get there eventually. So this function, e to the x, is called the natural exponential function. The natural exponential function. And its graph looks very similar to 2 to the x, because notice it's just a little bit bigger than 2. It's a little bit bigger than 2. So it looks very similar to your doubling function. And the only way, one of the ways you know right away that it isn't the doubling function is when you go to your point 1. What's the value of y, or f of 1, is not 2 anymore, it's e. 2.7. It's very close to 3 right there, right? 2.7183. We really couldn't distinguish. It's just that you know this is e. It always will go through 0, 1, just like all other sort of exponential functions, where we have 1 as the coefficient out here. And so that, again, it looks just the same. It has, the domain is all real numbers. Its range is 0 to infinity, not including 0. So the range is all positive real numbers. Very similar feel to it as 2 to the x or 3 to the x. Okay, so we can use our information for transformations just like we do for all of our other functions. So here are 4 functions, and they've been transformed from the parent function e to the x. So basically, I want you to look at these 4 graphs. Now note the lighter graph, this lighter graph here is your parent function e to the x. I'm just going to put it in red. Okay, this is e to the x. So I want you to look at each graph, figure out which transformation has been performed, and match these letters A, B, C, D with each of these graphs here. Okay, so you'll have some time working in your groups to do that. Okay, so let's talk about these together. So can we write in, can we describe each one of these, what transformation has happened to e to the x, and then we'll match it up. So with A, what kind of transformation have we done in number A to e to the x? Horizontal, because we're acting on the x value, right, the inside, so to speak. So horizontal, shift to the left, 2 units, right. So shift left, 2 units, okay. What about B? How are we acting on B? Outside or inside our function? Outside, because there's f of x, there's your original function. So we're doubling all of the outputs. That's a vertical stretch, right? Vertical stretch. And anytime we talk about stretches or shrinkings, it's always by a factor of 2. That's how we would describe that. C, are we acting outside the function or inside? Outside. Anytime you can put parentheses around your original function and whatever's happening is in front of it or to the right of it, you're outside your function, right? So how do we describe this one? Vertical shift down. Down 1 unit. Okay. And then finally, D, again, we're outside the function. So what are we doing to this thing? Shrinking. Which way? Vertical shrink by a factor of 1/2. Okay. So would someone like to just sort of think out loud about what was the first, where they started first? What was the first one that was, say, easier for them to identify where they started? C, you started with C, which is a vertical shift down. So you're literally thinking about e to the x and just picking it up and shifting the whole thing down 1 unit. So instead of it going through 0, 1 and 1e, it's going to go through what? If you shift it down 1 unit. 0, 0, and then e minus 1. Okay, so look for something that goes through the origin. Ooh, this goes right through the origin. So this is e to the x take minus 1. So that's what number was that? C? C. All right. So we've got that one taken care of. Okay. Let me check that one off. Done. Okay. Then where did you go from there? Someone else? You went to A? You went to A? Okay. So A, you're looking for a horizontal shift 2 units to the left. So you're looking for a graph that moves. Again, these shifts are like just picking them up and plunking them down. The shapes are exactly the same. And where did you find A, Orlando? Number 3. So if you compare this function to the parent function, the whole thing has just been shifted over. Did you have a particular point you were looking at here to help you? Yeah, 0, 1, right here? Yeah. All right, and if you notice that got moved over 2 units to the left. Right, so that was A. And so now you've almost through a process of elimination. You can almost get there. And then what was next? You had two vertical stretches and shrinks. You had a vertical, two vertical transformation, a stretch and a shrink. So now you just have to see right here, the 0.01 went up to 0.2. So your Y values got doubled. So you definitely know that that is B. And then by a process of elimination, this has to be D. Notice your Y value is half of what it was. Here's your sort of key point we look for on our exponentials, and now we're at 0, 1/2. So that got multiplied by a half. Okay. So that finishes up lecture 34. So let's now take a look at today's material. So let's see, Eric usually starts us off, and I usually, let's see, Orlando, why don't you start us off today?
That was a brief summary about the brief functions. And 120 bucks is the first function.
Okay, that's good. B, someone else? Liza? Yoo-hoo! Okay, so these are all the things that we sort of summarize from inverse functions. Okay, C, Tiffany?
The domain of F is the range of
Okay, it's not F of 1. How do we read F? Well, how do we read that notation? F inverse. So start again and read it as F inverse.
domain of F is the range of F
Woohoo!
and the range of F.
Okay, good. D, anybody? Right. Remember we talked about the X and Y just shifting roles? The input becomes the output and vice versa. And finally, Logan? Okay, that's good. So remember, we called this was the definition of what, when we were trying to check to see if two functions were inverses of each other, we composed them, we changed the order of the composition, and we came right back to X. Remember, this is what I referred to as the round trip. You come right back to where you started. Okay, that's the beauty of inverse functions. It's the major property that we look for, and it's how we define them. Okay, so this little quick summary of inverse functions is going to help us today when we try to find the inverse of exponential functions. So let's recall, we actually did this, I think, on Monday. We talked about this, that here were our two functions we looked at, the doubling functions where your base was 2, the growth factor is 2, and then we looked at the function where our base was 1/2, a decay function, and we said that this will have applications when we do half-life applications later on. And we talked about these being 1-to-1 because it passes the horizontal line test. I recall Monday we had a little like we had to kind of go up to the attic and use a duster to get back to that point. But we all eventually came up that both of these functions pass the horizontal line test, which means they're both 1-to-1, so these both have inverse functions. So let's take a look at the inverse function for 2 to the x and how we're going to get that. So let's use the idea that we talked about where we basically just swap the inputs and the outputs. So let's look at some key points on 2 to the x. Let's look at the table, and then we're going to just swap them, the x values and the y values. So here we are, f of x. Okay, so let's take a couple of negative points and 0 and a couple of positive points. So if I put in -3 for x, I get 2 to the -3, which equals what? What's 2 to the -3 equal? 2 to the negative 3. 1/8. It's 1 over 2 cubed, which is 1/8. So if I was to plot that, I would almost look like I'm on the x-axis. There it is right there. 2 to the negative 2 is 1 over 2 squared, which is 1/4. 2 to the negative 1 is 1 over 2, which is 1/2. So here I am at a fourth. Here I am at 1/2. And then 2 to the 0 is 1. That's one of our key points we look for, 0, 1. So I'm going to put that on there for sure. 2 to the first is 2. That's one of my other key points. When my exponent is 1, whatever my answer is, that's got to be my base. 2 to the 1 is 2. And there's my base. 2 squared is 4. Here I am at lovely 4. And then 2 to the third is 8. Here I am up at 8. Okay. 2 to the third is 2 to the third, which is 8. When x is 2, I'm 2 squared. Notice I'm just keeping them in exponent form for a minute. All right, so my points are negative 3, 2 to the negative 3. Negative 2, 2 to the negative 2. Negative 1, 2 to the negative 1. 0, 2 to the 0. 1, 2 to the 1. 2, 2 to the 2. 3, 2 to the third. So I'm keeping them in exponential form. Notice the y values are all exponential form. I'm not simplifying them. And there's a purpose, there's a reason for my madness here, okay? I'm not calling this 1/8, 1/4, 1/2, 1. I'm just keeping them in the form of the function. All right, so now we don't know what the inverse function is yet, but we can plot it because we know how to plot inverse functions. We know that it reflects across the line the identity function y equals x, f of x equals x, goes right across this line. Okay, it's the same distance right across that line, right? All right, there we go. So if 0, 1 is a point on my function f, what's going to be, here's my inverse function. I don't even know what it is yet. I'm just going to plot my points. So if I have the point 0, 1, what's going to be the point on my inverse function? If I take this point right here, 0, 1, what will be the point on my inverse function? 1, 0. I just switch roles, right? So 1, remember, was 2 to the 0, right? 2 to the 0. That's 1, 0. So I come right here, 1, 0. All right. So I'm going to actually keep it in the same form, 2 to the 0, and notice my answer, 0. My point 1, 2, when I reflect it over this line, I go the same distance. It's going to be the same distance to the line. The point 1, 2 is what is my new point now on my inverse function. 2, 1. I just switch roles. I just switch my inputs and my outputs. So I'm just going to keep this in exponential form. Okay. So I put in 2, 1. There I am right there. And now my point 2, 4, or 2, comma 2 raised to the 2 power becomes what on my inverse function? Someone other than Orlando, 4, 2. I'm just keeping it as 2 squared. So 4, 2. Here I go, 4, 2. All right. Someone other than Orlando want to tell me the point that corresponds to 3, 2 to the third, or 3, 8 on my inverse function? Right, 2 to the third, or 8, 3. Okay. So at 3, I'm going to be 8. Where am I? Here's 3, and where's 8 up here? Okay. It doesn't look right because I'm not at 3. Thank you, Linda. It's supposed to be 8, 3, not 3, 8. 8. And where's 3? I can't even see. Here I am. Okay. All right. So far, I've got the beginning of my inverse function. Kind of looks like this. Okay. Somewhat like that. Now let's take care of my negative numbers. When I'm -1, I was the number 1/2 called 2 to the -1. So now I'm going to be 2 to the -1, -1. So 1/2, -1. So I'm going to go halfway between 0 and 1 and go down to 1/2. There I am. Oops, too close. See, my pen is thicker than, I'm going to go down to, at 1/2, I'm going down to -1. There I am. All right. And then at 2 to the -2, at 1/4, I'm going to go down to -2. Oh, I'm going to get closer to the y-axis. There I am. I'm closer. And 2 to the -3, I'm going to go down to -3. It's actually going to look like I'm on the y-axis now. All right, so then I come down like this. Really, I hug that. All right. So there we go. That's the inverse function of e to the x. Okay, that's the inverse function. And you notice that every point, if you went right across that line, every point would be equidistant from the line. Okay. All right, so that looks like it reflects over that line. Okay, we feel pretty good about that graph. But let's look at the round trip business. If I start off with -3, I put it into 2 to the x, I become 2 to the -3, which we usually refer to as 1/8. Then I put 2 to the -3 into my inverse function, which we still haven't defined yet, and notice I come back to -3. Okay? And you see that where you started is where you ended up once you put these two functions. When you composed these two functions, you came right back to where you started. So you know you're doing this right. You just don't know what to call the inverse function. But does anybody see a relationship between the inputs of your inverse function and the outputs? If I just had you look for a pattern, if I had you look for a pattern here with all of your inputs and then what all your outputs look like, could anybody tell me, or do you notice, can you discuss it together briefly, what the pattern is between the inputs and the outputs? Okay. So you don't see anything? Oh, you're just saying no to Nathan? Oh, he was being sarcastic. Okay. So if each table has found a pattern, would you please put up your flag? And if you haven't found a pattern, maybe a table will help another table. Okay, all the flags are up. Okay, all the flags are up. So what did you notice? What does this inverse, so here's my question. What does the inverse function do to all of the inputs? What does it do? What does it do? Or how do you go from the input to the output? The output, so listen to my language. I lift off the exponent. Do you see it? I just lift off the exponent. I lift this exponent off and I put it right here. I lift this exponent off and I put it right there. So I literally lift off the exponent. So our inverse function is that I lift off the exponent. I lift it off. So far we've got this. Lift off. Lift off the exponent. So we're almost there. Lift off the exponent. So how did we find inverses before? We would have this series of steps we would go through, right? So let's start. We know f of x, let's say we have 2 to the x. We call f of x y, and we go 2 to the x, and we learn to find our inverse function. We swap our x's and y's, so let's do that. We swap our x's and y's, so x equals 2 to the y, and then we solve for y. Okay, no problem. Solve for y, what are we going to do? Gong. Does anybody know how to solve that for y using the methods that we've talked about up to this point in class? Up to this point. Only methods that we've talked about up to this point. Square root of y? How do I take the y root? The y root of 2. Okay, the y root of 2, the y root of this, and the y root of that? That would give us the y root of x equals 2. Okay, now how do I solve for y? Now I raise both sides to the power of y, and where am I? I'm right back to where I started. Okay? Okay. So, yeah, maybe there's something else we have to do. And in fact, we don't know yet how to undo that because we've never solved an equation where our variable is in the exponent. We don't know how to do that. So, we can't undo 2 to the y using any of the methods we've discussed so far in class. So, Caitlin wrote this phrase here, and I kind of like it. She says, go with me here. Just try to go with us. We call the thing that undoes 2 to the y. In other words, we found all of the points, or some of the points, not all of them since it's infinite. We found a way to find this inverse by lifting off the exponent. We've called it f inverse of x. We now have a totally different notation for that inverse. That inverse that lifts off the exponent, that takes the exponent off of this function here. Let's call this f of y equals 2 to the y. The notation for that is log base 2 of y. Log base 2 of y. So if we take this away, log base 2, this is the inverse function. So instead of writing in f inverse, we can write this. So what does this mean? All right, this is what the inverse function would look like for f of x equals 2 to the x. This is how we write it, log base 2 of x. And we're going to spend a lot of time with this over the next 15 minutes. All right, so that's why we're just saying, go with us here. Now, what do you notice about notice that the base here, that's what we call our base, or before we called it our growth factor. Notice the base of the log is right there. Same thing, it has a little subscript. Right? It has the same base, log base 2 of x. So let's see how we actually evaluate these. Here's the definition first. We know that the domain, let's go back to our graph. We know that the domain for this function, our inverse function, has to be the same as the range of our original function. The range of our 2 to the x function was all positive numbers. Notice where the domain starts. Can't put a 0 in here because there was no 0 as an output here. So the range is all positive numbers. And remember, the domain for my original function is the range of my inverse function. The domain for f of x equals 2 to the x was all real numbers. So we get except for 0, right? And same is true here for the range. Is that right? Did I tell you a lie? What's the domain for f of x equals 2 to the x? All real numbers, right? There's no restrictions on what we can put in for x. Therefore, there's no restrictions here on the range. It's all real numbers. You guys sometimes let me get away with lying. Okay. All right. So here is, we say that these two equations are equivalent. And it's going to take us a little while to look at these. And we could also say, look, that these two equations are equivalent. 10 divided by x equals 5 is the same as 10 equals 5 times x. Those are equivalent equations. You can get from one equation to the other. The same is true with these two equations. If you have y equals log b of x, That is equivalent, so I use a double arrow. That is equivalent to b to the y equals x. So let's take a look at the two and see how we can make sense of this. Go back to what we just did. Think of 2 to the third, or 2 to the negative 3, or 2 to the 1. Okay, that's what we're looking at here. We're looking at some kind of exponential function. Notice both on, this is called our exponential form, right? Exponential form. And this is called our logarithmic form, log form. Notice on both of these, the bases are exactly the same. Bases are the same. If I lift off this exponent, like we did before, if I lift off the exponent, it's the answer to my log equation. I lift off the exponent. Notice the output for my exponential, the output is the input for my log, because these are inverse functions of each other. So the output of my exponential is the input of my log. The input of my exponential, which we call the exponent, gets lifted off and is the output of my log function. They're just swapping roles. Now, you can get all like bugged out and weirded out about this new symbolism, log and all that. But remember, a log, all this fancy notation, is just equal to an exponent. A log is simply the exponent of your original exponential function. Okay, for each of your inputs, you're finding the exponent that would give you that particular value. So when I first learned logs and my mind would go like, well, every time I looked at them, I just remembered one equivalent equation. And then I used to write it on the top of my paper all the time. And this is what I used to write. 10 squared equals 100. That was my exponential form. Just so I wouldn't get all wigged out every time I looked at this. So I'd put this on the top of my paper. I was fine with that. Now I want to write an equivalent log form to this. Can anybody help me? What goes where? What base am I working on? What 10? So that becomes my little subscript. Now remember, my input to my exponential, here's my input. That's my input. And here's my output. So in other words, if I was looking at a point on the graph of 10 to the x, 2 would go in and 100 would come out. Another way to write 100 is 10 squared, right? So now my output becomes the input for my log. My output is 10 squared, or right, I can write that as 100 or 10 squared. And I just lift off my exponent. There it is, 2. So log base 10 of 100 is 2. Why? Because 10 raised to this power, because a log is just a power, 10 squared brings me to 100. So they're just equivalent forms of the same equation. And it just takes a little bit of time and a little bit of experience with you just working problems to get used to logs. Now notice how I wrote this log. You can write it as 100 here, or you can write it as this base to a power, and then it's really easy to evaluate because all you have to do is pull off the power, lift it right off. Okay. Now I'm going to just skip ahead for a minute. You never really write log base 10. This was just my way of remembering this when I was in school. But 10 is such a common base in mathematics, base 10, right? That we don't even bother putting it in. It's called the common log. When you have base 10, you just write it like this. Log 100 equals 2. We don't even bother putting in the base. It's understood to be there. I'm just going to put it in dotted like that, just so you can see it. So if you see a log and you don't see the base, it's understood to be 10. Okay? It's understood to be 10. So let's play around with a few of these. Write each equation and oh, what did I forget? Oh, it must be on the next page. So our directions is to write each equation in its equivalent exponential form. So I'm going to give you a log, and we're going to turn it into an exponential equation function or equation here. Okay. So here's a log. Now you look at this and you go, ah, what's going on, right? The output of a log is just an exponent. That's all it is. This is an exponent for power. That's all it is. And who belongs to this exponent? What's the base of this exponent? The same as the base of the log right there. So the equivalent exponential form of this is 3 raised to the second power is equal to 9. Notice the output here is the input for my log. Output of my first function exponential is the input of my log function. The input of my exponential function becomes the output of my log function. There's lots of ways to think about it. The other thing you can do right away is you can write 9 as 3 to a power, like this, 3 squared. And now all you do is lift off the exponent. Whoop, there we are. So if you can rewrite your input for your log as whatever your base is to a power, then you just simply lift off the exponent. All right, let's take a look at this next one. We want to put this from log form to exponential form. What's the base of my exponential form? What's the base? 8. Okay, same base. Here's my base. What's my exponent? -1. My exponent is the answer to a log because a log is just an exponent. 8 to the -1 equals 1 over 8. We're kosher. We're right back to where we started. All right. So that's how you translate from log form to exponential form. I'm just thinking back to a class I had when we used to be in the East Building, and I had a student, and the student had some challenges and had a aide in class with him, and I kept, over that 2 or 3 classes, I kept repeating that a log is just an exponent. When you see a log, the answer is just an exponent. And at one point, he got so frustrated with me. He said, "Would you stop saying that?" So funny. I'm sorry. I just had this like moment of remembering that. And my other students were like, "No, she can keep saying that because we don't get it." But it was just very funny. One of those moments that I should just keep to myself, I guess. What do you write in texting? TMI, too much information? All right. Okay, let's try to take this equation and write it in logarithmic form. 2 to the third equals 8. 2 to the third equals 8. So I don't know about you, but the first thing I do is I identify my base. What's the base of this exponential? The base, 2. That becomes the base here. All right. It's all right. The output of my exponential, 8, becomes the input of my log function. And notice, if you write 8 like this, your answer is almost like flashing at you like neon lights. What's my exponent? This is saying, what power do I have to raise 2 to get 2 to the third? Here I am. I'm looking at you right here. Just lift off my exponent, 3. And you can always check. 2 to the third brings you right back to 8. Okay, so you try this one at your seats. Try writing this in log form. Okay. Try writing that one in log form. Look at this. Someone want to volunteer how we write this in log form? Someone that maybe hasn't contributed today? So I get to hear your lovely voice? Yeah, I don't want to hear yours again. Cecily? Okay, does everybody agree with that? No? What's the problem? We have a revolt going. Okay. What's someone else want to give me another answer and then we'll try it? We'll talk. Okay, Eric, log base 6, 136 equals -2. Okay, so we could take this to a vote, or we could just try to see what's going on here. Okay, we said a log equals an exponent, or the power of your exponential. So whatever is on the right-hand side, in this particular case, the right-hand side, must be the exponent of your original exponential equation. So notice 6 was raised to the -2. That was our input on our function f of x equals 6 to the x. We put in -2. When we put -2 in, out comes 6 to the -2, which we write as 1/36. So the input becomes the output of my log function, that goes here, and the output of my exponential becomes the input of my log. So I'm taking the log of 1/36, base 6. My answer is the exponent I have to raise 6 to in order to get 1/36. Again, if you write 1/36 like this, 6 to the -2, boom, lift off the exponent. You're done. Are you all set with that now, Cecily? Okay. All right, so here's our answer here. Okay, I like it when people get different answers because then we can discuss what happens. All right, so we got a little bit of practice with logs going to exponents and vice versa. So let's take a look at these. Here's some more with different bases. So now I'm asking you to evaluate each of these logs. I want you to tell me what the answers are. You get 3 answers here. And when everybody at your group is in unison, put up your flag. If you have any questions, let me know. Okay, so let's take a look at this. The first problem is log base 10 of 100. If you can write your input into the log, the input into the log is the number 100. If you can write that as 10 to a power, your job is done for you. 100 is 10 squared, so all you do is lift off the exponent, 2. How do you check a log? You check it with an exponential. So you say 10 raised to the 2 brings me right back to 100. These check. I'm doing a good job. All right. Log base 5. If I can write 1/125 as 5 to a power, well, it's got to be a negative power because I'm looking at the reciprocal of 125. And so 5 cubed is 125. So this is 5 to the -3. So I just lift off my exponent, and my answer is -3 because it's looking for the exponent that you have to raise 5 to get 1/125. You check it by saying 5 to the -3 is 125. You check. Log 36 to the of 6. So now we're trying to figure out what power do we raise 36 to? What power do we raise 36 to get 6? So let's think about this. 36 can be written as 6 squared. So what do I have to multiply 2 by to come back? What power do I have to raise 2 to? So when I multiply these powers, I come back to 1. 1/2, right, because the square root of 36 is 6, so my answer here is 1/2. Because 36 to the 1/2 power is the same as the positive square root of 36, which is 6. Okay, any questions on those 3? Okay, so Ian, you said you made this easy peasy. How did you make it easy peasy? So basically taking each of these inputs and writing it in terms of the space, that made it easy peasy. Okay, all right. So with the log 36 of 6, to make it easy peasy, you have to write this thing as 36 to a power, which is 36 to the 1/2, and then you lift off your exponent. Okay? So this is called the liftoff function in my mind. When I think of logs, I think of lifting off the exponent of whatever's in here. I rewrite it in exponential form and just lift off the power, because that's all you're finding. The output is always the original input, which was your exponent on your exponential function. That's a lot of language, but with some practice, it will become more familiar, as most of this stuff. Okay, so we've got some basic log properties that you need to like become familiar with, because this is going to help you graph. These first two are going to help you graph the log function. Okay, so this first one says, if I write b here, what's the exponent on b? My input of b, not my base b. What's the exponent? 1. So what's my answer going to be here? 1. And how do you check? You say, I take my base of my log, which is b, I raise it to the exponent, that's my answer, my output of my log function, and I better come back to my input. All set. Okay, no problem. Okay. Now, I need to rewrite 1, if I can, log base b. How can I write 1 so it's b to some power? 0, right, because any b to the 0 power is 1. So now my exponent, my answer is 0. Okay. So these will help you with the graphs in a little bit. Now, these next ones really mess with your mind in terms of how they look. Not so much C, but D really messes with your mind. And all it is, before you even look at them, is remember when we used to do this? F of F inverse of X brings me right back to X, or F inverse of F of X. When I compose these and I reverse the order, I come right back to the beginning. So before we go down here, think of F of X as b to the X, and think of F inverse of X as log base b of X. Those are my two functions. So if I put F inverse, which is log b of X, into my exponential function, what's it going to look like? If I say F inverse of X composed with F of X, that says, oops, it's going to look just like D. Where I see X, I replace it with my log base B of X. This is just this composition right here, F of F inverse of X. My answer is X. The first one is when I put F of X into my inverse function like that. I literally take B of X and I plop it right into here. So log base b of b to the x, you just lift off the exponent, is x. So these are two properties that when you see them, they're like, ah, but they're just the two functions, the function and its inverse being composed, and your answer is x. So if you want to see something really funky, let's look at this one for a minute. Let's take the year 2013. And I raised 2013 to log 2013 of x. And you could be looking at that forever and saying, oh my God, what's going on? But this is just your exponential. Just think of this as 213 raised to a power. That power happens to be the inverse of your exponential function. And so your answer here is just x. You just come back to where you were. And if you had this log of 2013 and your input's 2013 raised to the x power, your answer is just x back again. So these are just properties that will help you when you're evaluating things if you recognize them. Okay, so we've already done the liftoff. C is already familiar to you because we've just played around with this for 3 or 4 or 5 problems where when you have the same base, you just lift the exponent off. This one is the one that kind of is a little funky to look at. It kind of messes with your mind a little bit. But again, it's just you're composing your two functions where your first function, your inside function is the log function, the inverse. Okay, and you're composing it with b to the x. And you just come right back to where you started because that's what inverse functions do. All right. So again, here's common bases. We've already talked about the first one. Your calculator only has 2 buttons for logs. You can't evaluate till you learn a little property. Anything other than base 10 and base E. Remember I told you base E was going to be a common base? So if you want to take, say, log base 10 of 1,000, here it is right here on your calculator, log. Let me quit this. Let me clear everything. So if you want to say log of 1,000, we know 1,000 is 10 to the third power, so our answer better be 3. Notice it doesn't even put the base in because it's understood to be 10. All right. Log base 10 of 1,000 is just written log because it's common. It's a common log. If your base, so we don't bother writing this. We just write log of x, and that means 10 to the x power. The 10 is hidden. Then you have to put it in. You have to put the base in. You mean how do we use the calculator? Another day. Another day. There's a little formula. All right. Now we write log base e of x, right? We never write log with a little e here. We use this notation, ln, because they think of Linda, right? ln, Linda, no. Log n, and it's, remember, e was called the natural base. So this is the natural logarithm. So it's ln x. When you see ln x, you know that the base on your exponential is e. You're looking at the inverse of your natural exponential function. Okay, now you say, well, why didn't they call it NL? Because the person that originally discovered this was French, and it was, you know, log de natural or something, you know, that's however you say log in French. But, you know, they put their adjective, the de natural, so that's why it's LN. And I could have made that up, but you could check me. Anyway, it's a good story. All right, and to do your natural log, that's this button right here, LN. All right, so if you take the natural log of 1, we hope we come back to what number? E raised to what number gives me 1? 0. So let's enter, and there's your 0. So if you want to evaluate common logs or natural logs, those are your 2 buttons to do it. All right, so let's see what's coming up next. So now I gave you some functions to evaluate with common logs and natural logs. So why don't we do a few together? How about A? What's the answer to A? I just did it. I didn't mean to do it. It's 3. Who yelled that out so quickly? Karis, thank you. How do I check this? Can someone tell me how I check this without my calculator so I know I'm right? That's right. I know it's base 10 because it's not there. It's common. Raised to this power 3 because my log is just a power brings me right back to my input of my log function. Thank you, Karis. Okay, who wants to try the next one? Logan? So, okay, so this says log base 10 of 100th is -2. And we can check that because 10 raised to the -2 is 1 over 10 square, which is 1 over 100, which is 0.01. Check. We're right back to where we started. ln e cubed. What's the answer to this one? 3. Notice you're already got the exponents just sitting there waiting for you to pluck it right off, lift it off, throw it down there. And how do you check? When you see ln, you know that the base of your exponential function is e. Here is your output for your log, which becomes the input for your exponential. And you're right back to where you started, e to the third. Okay. So now to help me make this easy peasy, I'm going to write 1 over e squared as e to a power. So how do I write 1 over e squared? It's the reciprocal of e squared, and I write that as e to what power? -2. And when I lift off my exponent, -2. Right, there's my answer. Can I figure out e to what power gives me 5? Do you happen to know e to what power gives you 5? I don't. So this is where your little calculator comes in handy. And you say ln of my input into my log function. Here's my input, 5, and the output is 1.609437912 forever and ever. And notice, how do you check? How would you check this on your calculator? This is your exponent. What's your base? E. So look for your e to the x button. Notice where it's located. Right above the ln function. That's a good word. Right above the ln button, because they're inverses of each other. So now if you raise this e to the x to this number, you better come back to 5 or you made a boo-boo, right? So I'm going to store that number. All right, I'll do the answer. So what do I hit first? Second e to the x, and then second answer, because this is the answer. I was going to just show a nice little feature, but that's all right. And you're right back to function, back to the original input of the function 5. Isn't that awesome? And notice what is the little thing right above the log button. See, you can tell your base here is the log is base 10, the common log, because that's the inverse right there, 10 to the x. So logs are just the inverse functions of exponential functions. And let's take a look at their graphs. We got about 7 minutes left, so we're not even going to get to the activity because I've talked way too much. So if you're interested, you might be interested in the logarithmic activity. It's called logarithmic laptops. You might like that, but I won't hold you responsible for it. But if you like to have something fun to do over Thanksgiving, you might want to try that. All right, so let's try to be serious for 6 more minutes, and let's look at the graphs of our exponential and our logs and see what we notice. Let's first take a look at the growth function when b is greater than 1. And Ian made the comment the other day when I was hurrying that my little note should have said b greater than 1 instead of 0 there. So here's an exponential growth function. We know all of these exponential growth functions b in the form of b to the x all go through 0, 1. So we know log base b of x is going to go through 1, 0. We simply exchange the inputs and the outputs. Same distance across from that line that it reflects across y equals x. So they're the same distance to the line or from the line. Okay, so if we were just looking at this function, the log base b of x, that's the red function here, what would be the domain? What would be the domain of this function? The domain of this red function. 0 to infinity, and soft brackets is your term, isn't it? Soft brackets or parentheses. Or you could just simply say all positive real numbers. That's okay too. But it's all positive real numbers. Because notice our function has no inputs over here. It's all positive real numbers. 0's not included because 0's not part of the range of my blue function, my exponential function. Okay, so all positive real numbers. What's the range of my log function? So where do I start? I don't know, way down here, or negative infinity, and where do I end? Positive infinity. So the range of my log is the domain of my blue function, which was all real numbers. So this is all real numbers. Is my red function 1 to 1? Yeah. Better be, because it has an inverse, the exponential function. Does it have any extreme or any turning points? Nope. Now, my blue function, my exponential function, had a y-intercept. That corresponded to become what kind of intercept? X-intercept. So it has an x-intercept. Notice my blue function, my exponential function, has no no x-intercept because I can never be 0. So my log function has no y-intercept. Okay. My blue function, the asymptote was my horizontal axis known as my x-axis, or y equals 0. What kind of asymptote do I have for my log function? X equals 0, the y-axis, right? Okay. Oh, you know what I meant to do. I know what I did. I see. Y-axis, so that's, what's the equation for the y-axis? X equals 0. Okay, the end behavior, as x goes to infinity, f inverse of x goes to what? Infinity. All right. Okay, let's take a look at a couple of transformations, and then I'm going to let you go. So this is the log function. What are your key characteristic points? Well, think back to your exponential function. 0, 1 was a key point on your exponential function, right? So 1, 0 is going to be a key point. If it goes through there, we know we're not doing any kind of stretching or shrinking. It's just your regular old log function. Then we had the point 1, and the point we got for e was the base. So if we had 1, 2, we knew it was a doubling function. If we had 1, 1/2, we knew it was a decay function with a base of 1/2. So we want to see, we go to our y value of 1, and then we can find what our base is. So here's our y value of 1. Let's see where we intersect. Oh, right there at 2. So this is 1, 2. Excuse me, 2, 1. 2, 1. So that tells me my base of my log is log base 2. So I know right now, just from those 2 points, that this function here is log base 2 of x. So let's see how I've transformed this function. Let's take a look at the first one. Oh, do I still go through 0, 1? I didn't even write that right. Nobody said anything. Oh, why didn't you, Orlando? It's 1, 0. Okay, so do I still go through 1, 0? Here, 1, 0, yep, that didn't move. This still looks like 2, 1. Oh, it's told me. Here is my original function. This is your parent function. And now we want to do a transformation. How are we going to transform it? We'll just write it, and then you can just graph it yourself at home. How has this been transformed? Are we inside the function or outside? Inside, it's going to be something horizontal. What does x plus 3, how does it shift it? What direction? Left. So that whole thing is going to shift left 3 units. Okay, what's going to happen here? What kind of reflection? Which way are we going? Right, reflection over the x-axis. So take a couple of points, maybe 3 or 4 points on this function, log base 2 of x, and move them or reflect them, and you'll get your new graphs. Hey, have a great Thanksgiving, folks. I'll see you on Monday.
You too, Gavin.
All right, I will.